As you can see from the heading here, the next bit of work that we're going into is about orbits. And I'll just mention here that what we're going to cover is basically just about Kepler's laws of planetary motion, so as planets orbit around the Sun. It's not really the full depth and breadth that you could go into when looking at orbital motion. So I just wanted to touch on the underlying aspects about orbital motion while we're looking at it, and then we'll get into Kepler's laws of motion as we go through. So the idea about orbital motion is that it ties together a few concepts that we've already had a look at, those concepts being circular motion and gravitation. So having an understanding of both of those is really important to then be able to actually understand how it is that planets orbit the Sun, or how satellites orbit the Earth for that matter. So if we have a look at what's going on here, the example being the Earth orbiting the Sun, and that in that situation, we're going to treat it initially as though that orbit is fairly circular. We'll see later on as we go through the rest of this video that it's not actually a circle, but to begin with, let's treat it as though it's a roughly circular path, and that means then that there's going to be centripetal force, and that centripetal force is provided by gravitational attraction. So that's the sort of linking those two ideas together to really get a good sense of how it is that physics works, I suppose. It's not just individual ideas in isolation, it's that we can actually draw them together and develop that into another area of focus. And so centripetal force here on Earth provided by gravitational attraction to the Sun. That means that we can do some things with the equations that are involved for both centripetal motion and gravitational attraction. So we know here that we're saying that the centripetal force is the same as the gravitational force. I'll just use the subscript G there to indicate the gravitational force. So we know centripetal force is given by the equation mv squared on r, and we know that gravitational attraction is given by capital G mm, where capital M would be the mass of the Sun, and lowercase m would be the mass of the Earth, divided by r squared. Now if we simplify, you can see that lowercase m is on both sides, so we can cross that out. We've got divide by r on the left side and divide by r squared on the right, so we can cancel that squared. So that means we're left with v squared is equal to g m over r. If we take that one step further, we can then say that the orbital speed is given by root g m on r. And so that basically means that we can conclude that orbital speed only depends on the mass of the body being orbited, and in this case that would be the Sun, and the second thing that it depends on is the distance from the Sun, or the distance from that body. So it doesn't matter about the mass of the planet or the satellite or whatever it is. If it's a certain distance away, it's then going to have a certain orbital speed. So there's just sort of the underlying ideas. What we really need to get to now that we've seen that fairly simple treatment, planetary orbits are a bit more complex than that. So they're a bit more involved, and fortunately the work to understand that's already been done for us, and that was discovered by Kepler in the early 1600s. And when he went through and did this work and discovered these ideas, he summarized them into 3 laws of planetary motion. We'll have a look at the first one in this video, and we'll do a little bit more in class to make a lot more sense of what each of these laws actually mean, because they can be a little bit tricky to make sense of, and there's even more behind them than what we'll necessarily cover but ultimately that's where we're going to be going for the rest of this video. So let's look at the first law, and I'm just going to call it, similar to how we refer to Newton 1, 2 and 3, I'm just going to call it Kepler 1. The summary of this, you could think of it as being the law of orbits. Now, as I mentioned earlier, we were treating the path that the Earth travels around the Sun as being circular. That's not actually true. All planets move around the Sun on orbits that are not actually circular. Those orbits are actually elliptical orbits. And one of the foci is where you would find the Sun. Now that word foci is the plural of focus, so we'll have a look at what that actually means, what the focus is, in order to make better sense of what this idea of elliptical orbits is. Now keep in mind here that that's another sort of fairly straightforward definition that you need to be able to state. So make sure you can jot down that wording almost word for word. Now, to explain what an ellipse is, it's a little bit easier to actually draw one than it is to just sort of be told what it is. An ellipse is basically just an oval shape, but it has some fairly strict conditions, and that is that it's traced by a point on a plane. So by traced by a point on a plane, we basically just mean on a flat surface, where the sum of the distances from that point to two other fixed points is always the same. So those other fixed reference points are the foci. So I'll just make that note in here. And we'll have a look at what that really means in a bit of a animation type idea to try and get that point across a little bit more clearly. Just before I do that, the other interesting thing about an ellipse, if you take a cone and you look at an angled cross section, that would also give you the shape of an ellipse. Let's go have a look at the this other representation. So here we have a point and two foci, so each one being a focus. Note that I'm really exaggerating this point to make it really clear what an ellipse looks like. When we start to look at what the orbits of planets actually are, you'll notice that they don't, the foci are not that far apart. We'll have a little bit more of a look at that in class. So if we consider that point over the right hand side, we're basically going to look at the distance from the point to each focus, and then we'll sort of make sure that we keep that the same. So as that point continues to move around, the distance from that point to each focus would be the same. So the path that that point is tracing out as it moves around those two foci would be the shape of an ellipse. Now, a little bit hard to see what that is without the detail being traced out as well, so let me add that path in. So you can see here that's the actual shape of the ellipse, and again if I just move that point around, you can see that the point sits on that ellipse. So that's the shape that an ellipse would make around the focus. Now again, to make it a little bit clearer to see, let's add the lines that join the point to each focus. So as the point travels around, you can see those two lines. So if we were to stop at that point there, the distance from the point to the focus on the left plus the distance from the point to the focus on the right would equal a particular value. So add those two together and we'd get some certain distance. If we then continue to a different point somewhere around the ellipse, so say over here somewhere, then that distance from the point to the focus on the left added to the distance from the point to the focus on the right would still be that same distance. So add those two distances together at any point on the ellipse and you would get the same value. So that's the definition of an ellipse. Now if I was to change those foci and replace them with one of them as being the Sun, and if we remove those lines, and if we change that point to be a planet, that would now represent the motion of a planet around the Sun. So as the planet moves, the distance from the Sun, you can see that increases and then decreases again as it gets closer to the Sun. So the orbit of that planet there is then elliptical. There's a little bit more we need to say about how that planet moves around the Sun. That'll be in Kepler's second law. But ultimately for the Kepler's first law, the planet will orbit the Sun on an elliptical orbit. Now there's just one last point I want to make about these elliptical orbits. There are 2 points that are particularly noteworthy to identify about an elliptical orbit, and that's the 2 points that are basically sort of at the extremes. So this point on the right in this diagram, and then on the left as well. So the 2 points, they have particular names. This one on the left is known as the aphelion, and it's basically the farthest point from the Sun. Now I'm mentioning these so that we can use them in the next law that we'll be looking at. So just 2 terms to be aware of. They're not things that you will necessarily be examined on, but just to be aware of what the names are. And the one on the right hand side here is the perihelion, which is the closest point to the Sun. So there's the first and probably the most straightforward of Kepler's laws of planetary motion. We'll have a look at Kepler's second law in the next video.